Hi everybody. My name is Omid. Today I'm going to talk about key verification anonymous credential with highly efficient partial disclosure. This is a joint work with Jan from Edinburgh University, Mahdi, Emad, Aysajan, Dave, and Bart from COSIC. So first, let's talk about anonymous credential system with partial disclosure and what it is. So imagine a person like Nick. He has some attributes like his full name, date of birth, nationality, national ID and job, and etc. And he wants to use these attributes to access to a service provider to gain access from it. For example, he wants to shop, or he wants to order something, or he wants to access a book from an online library. And this service provider, for example, this online library, needs to know your nationality or whether you're a student or not. Then it gives you access to the services and will provide you with the books you want. So from user perspective, we need privacy because the user doesn't want to reveal more information from himself, rather, just only about its nationality and whether it's a student or not. And he doesn't want to reveal other things like his national ID or full name or etc. But for the service provider perspective, it needs security. So it needs to know that the user doesn't lie. So for sure he's a student and his nationality is American, for example. So for handling the second property for the security, we need to add a central authority that we trust, like an issuer, to generate the credential for your attributes. So you just so first the issuer verifies that you indeed have these attributes, and then if you have it, it just generates a credential, like digitally signing a hash of your attributes and send it back to you. So what anonymous credential enables us is that whenever the user wants to prove that he has this credential, he can do it blindly. I mean, he can do it in a way that it's unlinkable to the original credential that it receives from the issuer. So for example, in this scenario, if the user wants to prove to the verifier that he owns a credential from the issuer, for a set of attributes that is superset of this nationality and job that it has. But he doesn't want to reveal anything more beyond that. So this is what anonymous credential enables us to do. So if everything goes right, the verifier gives access to this student, and this student can have the books he likes. And so there are another schemes which are key verification anonymous credential. So in the previous one, the verifier could be any authority that has the public key of the issuer. But in some scenarios, like for example, building management, for example, university has some doors that some sort of people only can have access to, or for example, another thing is public transportation. There is an organization selling tickets to the users, and for example, this user can have, in some zones, he can have access to public transportation. So in this kind of settings, in this kind of scenarios, we can say that verifier and the issuer trust each other, or maybe in other scenarios, the issuer and the verifier are the same entity, so they can share the secret key both for the generating the credential and for the verification. So for example, for the building management scenario, the attributes would be, for example, the name of the user and the door ID that he can have access to. And for the a public transportation one, his name, the zones that he has access to, and for example, the dates of the dates that his tickets is valid for. For example, if I want to, and this partial disclosure thing is really important here. For example, if I want to use my ticket in zone A and I want to use it today, the only thing that matters for me is to just disclose these two attributes and nothing more. So you might ask why we don't go for this for that publicly verifiable anonymous credentials. The reason is that the thing we can get from this kit verification anonymous credential is more efficient than what we can achieve from its publicly verifiable counterpart. So this is the motivation, the whole motivation of this work. I mean, working on this KVAC and make it more efficient. So today, first I talk about KVAC, have an introduction about it. Then we talk about the current gap in the literature for KVAC. And then for solving this problem, we propose two constructions. And I'm going to talk about it from now on. So let's get back to publicly verifiable anonymous credential. So in publicly verifiable anonymous credential, we have an issuer with secret key and public key. And we have the user that has access to the public key. So together, they run an algorithm issue that at the end, the user will be provided with a credential, and the issuer for generating this credential uses its secret key. And whenever this user wants to reveal it to the verifier, it generates a show by running the show credential, and the verifier at the end only receives the subset of attributes which we call D. And this verifier runs an algorithm verify credential, which returns 1 if this showing is valid and 0 if it is not valid. And the only thing that the verifier uses for that is the public key of the issuer that everybody knows. So by that we can have meet two security properties. One is unforgeability and the other one is anonymity. Unforgeability says that not having a credential for attribute set A, which is superset of D, the set that we want to reveal, want to disclose. If we don't have that, we are not able to generate a valid show for that. And the anonymity says that the verifier should not learn anything beyond the fact that this user has a valid credential, and it has a valid credential on an unknown set, which is a superset of D, and that's it. So let's do it let's turn it into the KVAC kit verification setup. For the kit verification setup, the only thing that we need to do is to give this secret key to both the issuer and the verifier, and there is no need for public key anymore. So we want to see if this simple solution, this simple construction, leads to a secure KVAC or not. As you can see, we want to show in the next slide that it's not going to happen because the unforgeability can be achieved. But the problem that we have is that with this construction, we cannot achieve anonymity. And the reason is that, so let's imagine that the issuer uses different secret keys for different users. So for user I, it uses ISKI, and for others different. And whenever this user I wants to reveal to generate the show for her credential, it sends the show to the verifier, and the verifier somehow brute forces all the ISK that it has. It searches among all the ISK he has used, and he figures out for which one of these ISK this verify credential returns 1. And if he finds that, he can easily link between these two users, and he can understand, okay, this user was the one who showed his credential. So in order to solve that, we have another property which we call key parameter consistency. In key parameter consistency, other than this ISK, we add another term, another value, which is IPAR, or issuer parameters. So in issuer parameters, issuer somehow commit on the ISK that he uses to generate the credential and prove to the user that he used the ISK, the same ISK that he has initially committed, for example, in the setup phase. And by doing that, this construction can achieve both unforgeability and anonymity for a KVAC. So, sorry? ISK, yes. Within IPAR, yes. In IPAR, yes. So by that, we can achieve both of these properties. And we have a KVAC, which is, as I told you, more efficient than publicly verifiable counterpart. And also, as a plus, we can achieve efficient pairingless construction, unlike AC. Because in AC, all we can get, and efficient is pairing based, and it needs pairing for the verification. So let's discuss about the gap that we have in the literature for the KVAC. For that, we need to go a bit more into the details of the KVAC. So as I told you, we have the user that has this IPAR and the issuer which has ISK and IPAR. So the issuer has all attributes that the user has, which we call set A, and generates a MAC. So instead of digital signature, we use MAC, which is message authentication code, using its secret key, and send tau and a proof. As I told you, now we need to convince the user that we use the same secret key for generating this MAC as we already committed to in the setup phase, which we called IPAR. So it's a zero knowledge proof, or NISC, non-interactive zero knowledge proof, that we have ISK as witness, and the statement is that ISK used in both of IPAR and tau are the same. But for that we need MACs which are zero knowledge friendly, which we call algebraic MAC. So an algebraic MAC you can explain is, for example, MAC GGM, which is something like this. So for example, if the message is A, which is a set A, which is A1 till AN, and the secret key is X0 till XN, the MAC on it would be two group elements. The first group element is something completely random, and the second one is the multiplication of the first element by X0, which is the first value of the secret key, plus the summation of all XIA. And this would be an algebraic MAC that is secure. So I forgot to mention, this was first mentioned in this paper, algebraic MAC and key verification anonymous credential by Melissa Chase and etc. And in the showing phase, what you need to do is to first commit on the attributes that you have, and then try to randomize the MAC that you have, because as you saw, this MAC that we have, for example, MAC GGM, is randomizable. So we randomize the MAC, and then in the showing phase, the user sends this randomized tag, the commitment on the attributes, and a proof that I have, because the only thing that the user wants to send is set D. It wants to convince the verifier that I know all the attributes A, and also the randomness used in commitment and the randomized MAC. And I know all of them, and they are all bound to each other, and there is no cheating going on. And that's what makes the whole construction unforgeable. But there is a problem with that, and also open for set D, which is the set that we want to reveal to the verifier. But there is a problem with this construction. So Nick asks, why should I spend size of A in communication and computation? Because as you can see, we have the whole set A as a witness for our zero knowledge proof. While I just want to reveal only a subset of the whole attributes. For example, if I have 100 attributes and I just want to reveal one of them, why should why my showing phase should spend order of, size of A, 100 attributes. So this is the problem that we wanted to solve in our new KVACs. So as you can see, this is a table of comparison between our constructions with other KVACs. And in this column, we have the presentation size. As you can see, all of the previous work have dependency N, have linear dependency on the size of the whole attributes. But for us, it's constant size for both construction that we proposed. One is pairingless and the other one is pairing-based. So let's go to our first KVAC construction. So our first KVAC construction takes heavy inspiration from this paper, which is structure preserving signatures on equivalence classes and constant size anonymous credentials. So in 2019, this is done by these authors in a publicly verifiable counterpart. They could achieve a constant size anonymous credential in publicly verifiable setting. So the thing they did was to combine two ingredients, like one is a structure preserving signature on equivalence classes, or SPSEQ. These are some specific digital signatures that enable the user to randomize both the message and the signature, and also a set commitment. They designed these two schemes and they combine them to have a constant size anonymous credential. So what we did for KVAC MEC, our first construction, was to turn all this to their MAC counterpart, to kit verification counterpart. So we designed a structure preserving MAC on equivalence classes, or SP-MAC EQ, and we turned this set commitment they had to a designated verifier one, which we call DVST, and we designed a constant size KVAC. So what is the idea? The idea is that, okay, in the issuing phase, we ask user to first commit on the attributes that it has, and then the issuer generates a tag for this commitment and also attach a proof of well-formedness for this MEC, and the IPAR that he previously committed to, and also the IPAR, which is the commitment of the ISK. And then in the showing phase, the user sends the randomized version of the commitment, the randomized version of tag, and an open value for subset D, which is something that shows to the verifier that the user has a credential for a superset of set D. So we have three objectives here. The first one is that C prime and WD should show that the user has credential for an unknown set A, which is the superset of D. And the MEC should be randomizable because we want to randomize it in this showing phase so that it is unlinkable to the issuing phase. And the size of C prime, tau prime, and WD, which is our show, should be constant size. So let's first talk about SP-MAC EQ. So SP-MAC EQ uses bilinear groups. So group 1, group 2, and target group, and we have a pairing operator which maps G1 cross G2 to target group. And the MAC is something like this. So if the message is C, which is C1, C2, has 2 elements, and it's in, and both of the elements are in group 1, and the secret keys that are field elements x1, x2 in ZP star, and P is the prime order of the generator for G1, and also G2 because it's symmetric. And the tag would be 2 group elements. The first one is A, which is a randomness, multiplied by x1 C1 plus x2 C2, and the second group element is A minus 1G, G2. So the first group element is belongs to group 1, and the second one belongs to group 2. So as you can see in the verification, whenever you receive a message C and a tag tau, the only thing that you need to do is to check this equation, whether the pairing of x1 C1 plus x2 C2 and G2 is equal to pairing of R and T. And it is the cool property of pairing that you can just move the coefficient of G2 from the second group element to the first group element, and they cancel out each other because you have A inverse there, and this verification holds at the end. And the other thing that is cool about SPMAC EQ is that you can randomize both message and tag in this way. So for example, if you have the message C1, C2, and the tag is R and T, which are in group 1 cross group 2, we have an algorithm which we call change representation. In change representation, we use a randomness mu to multiply both terms of both elements of the message by that randomness. And for the second one, we multiply the first element by mu, and we also use another randomness, which is psi, and we multiply it by the first element, and we multiply the inverse of it in the second group element, because in the verification, we need that these 2 group elements at the end cancel out each other. I mean, in these 2 randomness that we use cancel out each other, and this tau prime at the end would be a valid MAC on this randomized version of the message. So with this, we can have this, the main properties of SPMAC EQ is unforgeability and privacy. Unforgeability says that you cannot generate a tag for a message that you haven't queried, but there is one thing that if the adversary generates a tag for a message that he has queried, but the altered message belongs to the same class of the queried message. So because of this change representation, the adversary is able to do it for other for other messages. So unless it's not like that, if adversary can forge something, he can be successful. But with this construction, the probability that he'll be successful is negligible. And for the privacy, C prime and tau prime should be completely unlinkable to the original message and tag we had. So using this SPMAC EQ, we can achieve our second goal, which was MAC should be randomizable, and also it should be secure. So in order to achieve the 2 other goals, we need DVSC. DVSC, or designated verifier set commitment. So for that, we first define a polynomial function f. So we say that f of x for set A equals to the product of all x minus a's, which A is a member of this set A, and when whoever that has this set A can easily find the coefficients for this polynomial, which is the summation of fi xi for I equals to 0 till size of A. So it's the core thing that we use in our DVSC. So imagine now that we have this user in the left side, the issuer on the right side. The issuer has the secret key V, and he also has a I pair, which is VIG for I equals to 1 to T, and T is the maximum number of attributes that a user can have. So the commitment then would be f of v for set A multiplied by g, which is equal to the summation of all fi vig. So this commitment can be computed by both sides. Why? Because the issuer has all the things, has the secret key, has the set A, but the user, and also the user can do that because the user knows about his attributes, so he can easily compute the coefficients fi. And also this VIG is provided by the issuer in the iPair, so it can use it to compute this commitment. So it's completely deterministic commitment, can be computed by both sides. And as you can see, we can have a commitment which is just one group element for, whatever is the size of the attribute. So it's regardless of the size of the attributes, our commitment would be just one group element. And in order to open for a subset D, which is D, which is a subset of A, the only thing that you need to do is first randomize the original commitment, which would be, for example, if you use mu, it would be mu f of v for A multiplied by g, and the WD would be the open value for that, which is mu f of v for set A minus D. G. And the thing that the verifier needs to do, because the verifier knows about D, the set D, and he also knows about V, he can compute f of V for set D multiplied by WD and see whether it is equal to C prime or not. And why does it work? Because as you can see, f of V multiplied by WD equals to mu f of V for D and f for set A minus D. And if you open that, the first one is the product of all V minus A for A in set D. And the second one is the product of all V minus A for A in set A minus D. And so at the end, you have mu multiplied by product of all V minus A for A in set A. And then at the end, you have mu f v for set AG, which is C prime. And it works. So we achieved all the things because, as you can see, this WD is again one group element, and C prime is also one group element. So at the end, you have constant size showing for your whole KVAC system. But there is something wrong with this construction, is that the verification needs pairing operation. So we wanted to look into how we can do it without any pairing needed in the verification phase. And this leads us to our second construction. So first, in order to show you how we achieve this construction, let's talk about why we needed this pairing in the first place. So in our tag, in order to make it unforgeable, we needed to add a nonlinear term A-1G2 in the second group element of the tag. So this avoids some attacks like meaningfully combining different credentials to forge a presentation for a set that the issuer didn't give access to previously. So we need this nonlinear term so that we avoid these combinations like adding different tags together so that we can achieve a valid tag. But this nonlinear term that we attach to the tag should be cancelled out in the verification using the pairing, because there are a lot of randomness going on. First, the issuer adds randomness. Second, the user adds randomness, and the verifier doesn't know anything about the randomness used. So these randomnesses should cancel out each other in the verification. So the question is it possible to avoid this attack without adding a nonlinear term to avoiding? avoid pairing? The answer is yes, our KVAC GGM construction. So what is the idea? Let's first talk about an insecure construction. So imagine that the commitment is easy, just f of v for set A multiplied by g, and the tag is simply multiplying the secret key by the commitment, and also we have this proof of well-formless there. So in the showing phase, imagine that the user just sends mu f a g and c prime, which is the randomized version of the commitment, top prime, which is randomized version of the tag, and also the open value that I told you in the previous slide for DVSC. So the thing that happens here is that we can have an adversary that uses two different credentials in order to, and combine them in a way to generate a credential for another set, which is not a subset of A1 or A2. And this would be an obvious attack. So the thing that we did was to make this simple construction secure. How we did that was to add a randomness to the commitment. So now the commitment is not deterministic anymore. For every user, the issuer generates a different, uses a different randomness value, y. And because now the user cannot compute the commitment anymore because he doesn't know about y value. So we also send a y multiplied by vig for all I equals to 1 to a to the user so that he can also compute the commitment. And then now, because if the adversary receives different commitments, different credentials, he cannot meaningfully combine them and compute a valid showing at the end because he doesn't know about y value. And then in the showing phase, it's simple. It's just we added this y to both randomized commitment and the open value for set D. So, so it is not, as you can see, this is not constant size credential anymore because the user needs to keep this y multiplied by vig because it needs it for generating this c prime and w prime in the, for generating wd in showing phase, but we can achieve constant size presentation and pairing free construction. So that was it. I wanted to just give the whole idea of our paper. If you want to go to more details, you can visit our paper on ePrint. Thank you.